Good afternoon. Before I start, may I ask a question? How many people of age 21 and under are in this room? Okay, quite a few. So I have a message for you at the end of the talk, so please stay tuned. So today I want to talk about relatively simple things. I want to talk about quantum mechanics of one or two particles in graphene, in single layer graphene and in bilayer graphene. So I'm from the University of Exeter. That's probably not the most famous university in UK, so let me say a few words. Exeter basically is near Devon County, so it's southwest of England. So that's a beautiful place which sometimes was a home to awful creatures. But we don't have anything like this at the university, so that's our building. We have nice view through the surrounding area. At the University of Exeter we have Andrey Shytov Center for Nanoscience, where we study graphene and other related things. And recently we established a center for doctoral training in metamaterials. So again, that's graphene-related things, spin transport-related things, magnetism-related things, electromagnetism-related things, that kind of business. All right, so that's a brief outline of my talk. So first, I'm going to remind you simple facts about bound states in quantum theory, and then I'm going to discuss interesting kind of bound states in bilayer graphene and single layer graphene. Okay, so. Bound states are important. They are all around us. There are bound states on cosmic scales, like the solar system. And what's more important to us, bound states of a small number of particles, protons and neutrons in atoms, and nuclei and electrons in atoms and molecules, and so on. A typical bound state basically is made of some particles, attractive force that holds them together, and normally you don't have a static equilibrium, so usually bound state is a kind of dynamic equilibrium, because in the case of electrons in atoms, static equilibrium is simply impossible, so particles have to move. If you start thinking about quantum aspects of this, then you might find out that simply having an interaction isn't always sufficient to form a bound state. So in quantum mechanics, we know that energies in hydrogen atom are quantized. So bound states only exist at very specific energies. And there are very non-trivial examples of bound states. So one which is particularly important for astrophysicists is known as Hollow state for carbon. The existence of this state basically is the matter of life and death. Coming again back to condensed matter domain, there are interesting examples of bound states formed by electrons in superconductors known as Cooper pairs. There are interesting kind of bound states known as Yefimov states for atoms in optical traps. So quantum mechanics makes the existence of bound state a non-trivial and a very interesting equation. Let me remind some really textbook stuff about bound states in conventional quantum mechanics. By conventional quantum mechanics, I mean massive particle, or as we say, quadratic dispersion, and some attractive potential U of So if you look into Landau and Diffritz or into Elias and Dissenbook, you'll find out that a bound state always exists no matter how big is the potential in dimensions 1 and 2, but not in dimension 3. Here is a well-known square well problem for a bound state. So suppose the potential is a square well, and we work in 3 dimensions. Then it turns out that the bound states only exist if the depth of this well exceeds some critical value. And as we see, this critical value basically is set by the kinetic energy of the electron, by the energy of zero-point motion of an electron confined to the well of size A. Right near the threshold, the wave function, however, has very interesting structure. So it changes rapidly inside the well and levels off at the well boundary. And that's basically the criterion for finding this critical depth. So basically, all this illustrates that the existence of bound state in simple particle quantum mechanics basically is about balancing quantum zero-point motion energy and the attraction energy. In many dimensions, in fact, quantum zero-point motion energy gets a lesser contribution from centrifugal barrier. And that's what makes 1 dimension different from 2 dimensions, from 3 dimensions, and so on. All right. So there are many kinds of bound states in condensed matter physics. There are true bound states such as donor or acceptor states in semiconductors, excitons. There are surface states in topological insulators, and for the first 2 examples, you can find out that that's a true bound state because the system has such as a semiconductor has an energy gap, and so if for some reason the energy of a quantum mechanical state falls into the gap, then you get a very stable state. It has it has nowhere to decay. In condensed matter, we also have to deal with different kind of bound states. Bound states from D and F magnetic impurities, for example, where we have an energy level placed inside the conduction or valence band, and the level hybridizes with the band, and so the state would decay. And these states are normally seen as wide or narrow, depending upon the coupling, resonances in density of states and another factors. All right. So now, what does this have to do with graphene? As you probably know, graphene is this chicken wire arrangement of carbon atoms. And what's interesting about this particular lattice is that it has 2 atoms in the unit cell. So there is extra degree of freedom in the wave function, basically which sublattice degree of freedom. One can show that under reasonable approximations of the time binding model, the spectrum of graphene has these conic points at the corners of the prevalent zone, and near these conic points, energy dispersion is linear, so one can describe the motion vector in electrons and graphene via this Dirac Hamiltonian. So the Hamiltonian is a 2x2 matrix because of essentially 2 sublattices, and it's linear in momentum near the conic points. All right. Can we create a bound state in graphene? Well, you can notice that in single layer graphene, the density of states exists both at positive energies and at negative energies. More careful inspection shows that the density of states is non-zero on the positive side of the charge neutrality point and the negative side, but formally it becomes zero right at the charge neutrality point. So charge neutrality point looks almost like a gap. Because of this, in principle, it's possible to take one state from the electron continuum and drag it into the whole continuum. Eventually, it will decay into the continuum, but that doesn't happen instantly. So there is a way to create a resonance there. These resonances were first discussed in the context of high-energy physics by Т.Г.Шевченка and Popov. 3 years ago, these states were in fact observed in graphene. In the tiny experiment performed in the group of microchromium. So Young Wang and Dylan both were Mr. measurements in this paper. So you can see that indeed in single-layer graphene there is it's possible to engineer a resonance state by creating sufficiently strong attractive potential, and the state is rather broad. What about other kinds of graphene? What about bilayer graphene? In bilayer graphene, where the two carbon atoms are stacked on top of each other, the spectrum is very different. The tunneling between the red layer and blue layer are reconstruct their point into two parabolic bands, so that the dispersion is now quadratic momentum, almost like in conventional quantum mechanics. However, there is a catch. So again, we have pseudo-spin-like degree of freedom for this Hamiltonian. So it means that the energy can be plus momentum squared or minus momentum squared. And so if you plot density of states, you'll find out that there is a positive energy continuum which describes electrons, and negative energy continuum which describes holes. And they overlap very well right at the charge neutrality point. So the density of states is non-zero everywhere, and apparently charge neutrality point isn't special. If I didn't paint this blue and red, you wouldn't be able to tell me where the direct point is. And so you might think that it's nearly impossible to create a bound state here, because continuum states, the states that could run away to infinity, are everywhere, and there are lots of them. If we try to create a bound state, a purity state in a system with such energy spectrum, the state would decay very quickly. It would hybridize with the continuum. The only way out would be to have this coupling to the continuum somehow suppressed. And interestingly, that's basically the case here. One can try to analyze bound states for bilayer graphene, that is on the formal level, for this system with this Hamiltonian. 2 by 2 Hamiltonian matrix and describing the electron, external potential U, assuming cylindrical symmetry which is a very popular approximation, and one can write the equation for the wave function. And here I try to separate the contribution from electrons and holes by using red and blue colors. So one can write the two equations for the two components of the wave function, and after some manipulation, one can notice an interesting property of these equations, which can be seen here. So you don't really need to understand what happens here. The important thing is that here the equation for the red function doesn't involve blue function, and the equation for the blue function doesn't involve red function. So there are two components of the wave function which can be completely disentangled, but only in one very special angular momentum channel. The channel for m equals 0. So here we have an electron with positive parabolic distortion, which experienced the potential U of R, and we have a hole with a negative parabolic distortion, or equivalently we can say that the hole experiences the negative of U of R. Here's what we get. You can notice, however, that the equations for the functions U and V are not standard Schrödinger equations in the S-wave angular momentum channel. So they differ by this -1 upon R squared contribution. If you try to figure out what's the role of this, you can actually find out that these equations describe two independent particles with angular momentum of ±1. So that's a P-wave. So you start with S-wave channel for the spin-off wave function, and you arrive to two independent equations, but this time in the P-wave channel. In two dimensions, sorry. In two dimensions, a bound state exists only for your potential strength only in the S-wave channel, but not in the P channel. In the P channel, you normally get a critical strength. So the potential here in these equations must be stronger than something for the bound state to occur. Here we see an interesting example of a bound state, which which is fully which could be electron-like state, fully submerged into a whole continuum, still not hybridizing with this whole continuum. You can ask, why does it happen? I think that's basically because electron and whole continua differ by the chirality of charge carriers. And there's this state which can be, which is similar to quark state in optics. And to see that chirality is really important here, one can consider a simple example of the states earlier considered by Mark and Andrey Shytov, the case of one-dimensional barrier, and there again you can show that a similar decoupling does happen, and it's related to the chirality of charge carriers. So the interesting thing is that this decoupling also happens for circularly symmetric potential, and circularly symmetric potential is better if you want to engineer this bound state, because then the existence of the bound state relies on discrete quantum number, the angular momentum channel. What we probe this? Well, probably the easiest way to probe such a bound state is by studying time density of states. So basically by performing the same experiment which I've shown you before for the density of states of electrons in single layer graphene. So here's my prediction. if you create a sufficiently strong circular symmetric potential, the density of state near this potential should look like this. There is smooth background from electron and Hawk continuum, and a sharp resonant peak describing the Hawk bound state. So how can one engineer this potential? Well, the formula for critical strength gives you some hint. You don't want a short-range potential created by impurity. So if A is very small, then you has to be big. So you want a smooth potential. An example of this might be quantum quarrels. So here is the STM data taken near a very large room formed by iron atoms. So my prediction is that if you create a quantum core in bilayer graphene and probe density of states by the STM measurement, you should be able to see a resonant peak. So another possibility is basically by considering gating bilayer graphene by an STM tip. So again, if you create a smooth potential by electrostatic gating, your width of the potential valve A becomes large, and it's very easy to make the potential supercritical so that it would host a bound state. Okay, so that was one story I want to tell you. Now let me go back to single-layer graphene and consider now the case of two particles in single-layer graphene. Suppose I have two particles, total momentum is 0. Then we can place these two particles into upper and lower Dirac cones so that the momenta are opposite. Let's turn on the interaction between the particles and see what happens. So you can notice that for total momentum of 0 for two particles in two opposite cones, kinetic energy becomes degenerate. No matter what is the momentum of each individual particle, if the energy of one of them is plus Vp, the energy of the other is minus Vp, so total kinetic energy is 0. That might sound like a derived formal statement, so let me explain what that means. You can notice that the two particles here sit on the same branch of Dirac spectrum, and it means that they have the same velocity. So you start with two particles in a configuration like this, and they have the same velocity, so they would move ahead or backwards, preserving this configuration. There is nothing that drives them close together or further apart. So this looks like kind of singularity, and now the question is this picture stable? As you can easily guess, this picture is unstable, so once you start changing the Hamiltonian this problem, you will no longer have this property. So let's see what happens if we consider deviation of the true spectrum in graphene from simple linear approximation, which is laid near the Dirac codes. Here are the two most simple terms that you could use to extend this Hamiltonian in graphene. So here is the standard linear distortion. Now let's consider the terms which are quadratic in particle momentum. There are two such terms. one term which isn't obvious but which is normally considered is this thing called trigonal warping term. It arises from the fact that graphene's lattice has 120 degree rotational symmetry. So you could get a term like this, which originates from nearest neighborhood. And there is a simpler but slightly less obvious term, P squared over 2m star, which is fully isotropic, which is pseudo-spin independent. And the version of this term could be next nearest neighborhood. So you can write this Hamiltonian purely looking at the symmetries, or you could do microscopic analysis starting from tight binding model, and this will produce exactly this expansion near the pure point, and this will give you the formula for the two effective masses, M star and M. Next there is neighborhood is a big effect, so the hopping is only 0.1, but there are 6 next nearest neighbors as opposed to 3 nearest neighbors, and the hoppings are longer, so eventually it turns out that this effective mass isn't infinite. Depending upon which source of data you trust, you get 6 to 10 ferrielectron masses. The trigonal warping term, which comes from nearest neighbor hopping, is more important, so the corresponding effective mass is smaller, but interestingly, the contribution of this mass depends upon which value your electron is in. So in particular, if you place one electron into K value and the other electron into the K prime value, you can essentially annihilate the effect of trigonal warping, and then you are only left with these two terms. So what's the effect of this term on the and respect of this bielectron pair? The naive analysis would be to write the total energy as the sum of kinetic energy of the first electron, kinetic energy of the second electron, and the repulsion between them. And in the total kinetic energy, the two linear terms would compensate. You are left with minus v squared upon m for your kinetic energy, and that would be potential energy U of r. And to solve this Hamiltonian, you can basically negate the overall sign of it. If you do this, you find out kinetic energy with the positive sign, and your Coulomb repulsion between electrons becomes attraction. You basically get your, as a solution to this problem, you basically get hydrogen spectrum flipped upside down. So your energy levels, instead of condensing at high energies, would condense at low energies. Of course, that means that these states are not in fact stable. They must be some kind of metastable states. But in principle, if you exclude all other states from the game, then that's the solution to this problem. However, if you put in the numbers, you soon start suspecting something. In graphene, you could assume that electron-electron interaction is partially suppressed by the dielectric constant of substrate, the dielectric constant of graphene. So interaction is weaker by a factor of maybe 10. But the effective mass m star here is again about 10 electron masses. So you get roughly the same anti-binding energy as in hydrogen atom of about 10 volts. And that means that this metastable state is pretty tight. It has the size of about the size of hydrogen atom, of about 1 or 2 angstroms. And that basically means that the whole picture is no longer constant. We assume that the state lives near the zero cones. Now we have found out that it lives somewhere near the band edge. And also, probably there is nothing wrong about a pair living near the band edge, but then we face a different problem. So if you say that the whole cone in a gold graphene is normally filled, then we cannot place one particle there. So we have to clean up this cone up to the band edge, and that would create a huge charge density, a huge spin response, and then we have to solve the problem completely anew. So we need, if you want to understand this further, we need to understand the effects of Fermi C. And one can think of 2 important effects of Fermi C. One is that neither of these particles can dive into the Fermi C because all states there are occupied. They are blocked through Pauli exclusion principle. And the Fermi C would screen Coulomb particle between the particles. It would suppress the interaction at large distances. So here we have a pair of particles and the Fermi C, which affects their binding energy. So that's remotely similar to what happens when you consider Cooper pair. So you start with 2 particles on top of the Fermi surface, and the fact that they can't go inside the Fermi surface modifies the binding energy. One can treat the problem fully scientifically by writing beta-salpeter equation, this set of Laser diagrams, and consider the interaction to be the sum of Blair-Coulomb interaction and spin-Coulomb interaction with polarization bubble, and so on. But one can in fact understand what happens here via much more simple way. So if we restrict the analysis to the sector of non-dispersing states for which the kinetic energies are opposite, if we say that the binding energy of the pair is sufficiently small, so we don't need to consider frequency dispersion of the polarization bubble, then we are back with a simple quantum mechanics problem. Kinetic energy, which is quadratic in momentum, and spin Coulomb repulsion. Spin Coulomb repulsion can be approximated as a delta White potential. So very simple quantum mechanics problem, but there is an important fact. The momenta available to the particles are constrained by the formal momentum of the system. So showing your equation with a Hamiltonian like this can be very easily solved in momentum space. Basically, the equation just becomes self-consistency condition, which has this form, and you can extract the energy of the bound state by solving this self-consistency condition. So you can notice that there are 2 effects of ferromomentum here. We have the numerator, which basically tells you about Pauli blocking, and we have the dependence on the interaction straight in the denominator. So that's the contribution of the speed. So you can then graph the resulting binding energy, and it's roughly linear in Fermi momentum. At small Fermi energies, it reaches the maximum at a certain point, and then spin becomes dominant when you consider really strong doping, really high charge density. So this regime, the proof is mostly determined by the spin, by this exponential. Then you can ask, okay, what are the you can't dope graphene in real experiments to arbitrarily high density. Where is the realistic boundary? Well, if you say that realistic boundary is somewhere 100 to 200 millivolts, it basically means that the energy of the bielectron state is on the bounded blocked segment of the curve. And so the energy of the bound state is roughly linear in Fermi energy. So it's about 1/8 of the Fermi energy. So 1/8 comes from two spins, two bodies, and any mathematical factor of now you can ask what are the manifestations, what might be the manifestation of these bielectron states. And here you can't get away with simple simple tools like quadratic Hamiltonian and so on. So here I have to be rather speculative. One thing is that this bielectron state is a bit like a Cooper pair, so one can hope that if you couple single wire graphene to superconductor, this could, in principle, indicate this could give rise to some kind of enhancement of proximity effect. It would be interesting to understand if they give rise to any optical response. The problem with trying to see these states in optics is that that's a system of two electrons, and the system of two electrons shouldn't have dipole moments, so it probably would work like a dark exciton rather than bright exciton. In principle, these states could lead to some resonances in tunneling, but for this you need two electron tunneling overcoming the contribution of single electron tunneling. So again, it's hard to say how realistic this is. Now let me say a few words. So one can ask, for example, if one can combine co-loc states in biwire graphene and this two-particle physics. So that's what I tried this summer with a local undergraduate, Igor Bondar. So basically, we were looking at Igor just finished his second undergraduate year, so we had to do some really simple things. So we considered two-dimensional square well as very simple and naive approximation for interaction between electrons in biwire graphene, and we try to find out either bound states or quasi-bound states. So one conclusion was that there are no true bound states. The chirality trick, which that decouples electrons and holes in single particle problem doesn't work here. But if the repulsion between the particle is sufficiently strong, you can identify quasi-bound states as resonances in the scattering phase. So in principle, that would be some interesting physics, but that's currently work in progress. So now my brief message to the younger members of the audience is that if you are in your second or third undergraduate year, you might think that you have to learn quite a lot before you start making useful contribution to physics. That's, indeed you should learn a lot, but in fact, often there are simple science questions, even in theory, which can be answered with relatively simple methods. So you can also try to make your contribution to the forefront of research. So don't be shy. Use the Use various opportunities available to you for summer undergraduate research and other such things. So Professor Leviatov explained this in his talk this year, and there must be slides from his past year talk available for your reference. So I want to encourage you to try your hands on the actual scientific research. And now the conclusion for adults. There are interesting kinds of bound states in graphene-based system. Single particle bound states in bilayer graphene, two particle bound states, two particle metastable state is single graphene, and maybe there are other interesting stories of this kind. Thank you.
Actually, I have two questions. The first one about the second half of your talk, when you pair the states from the different columns. In principle, there is an overlap integral if you don't use the type-binding approximation, and then there are even experimental data, T.G.N. experiment, which shows that even the Fermi velocity in the upper and lower cone are different. So what's the effect of this on your result?
So are they different right at the zero point, or are they different at finite energies?
Well, I don't remember, but because it's linear, it means that there are different Fermi velocities for upper and lower cone.
Yeah. Probably any asymmetry would do, and then one might look into details. Which asymmetry, quadratic or linear, is more important for a particular value of momentum. So that's probably all I can say.
Okay, thank you. And the second question is about your bilayer part. So you use an effective Hamiltonian with quadratic dispersion. Did you try to estimate what would happen if you use full bilayer model with first order differential equations? So for components.
Yes. So in fact, to generate this picture, I included the linear term. So in bilayer graphene, there is also a linear term coming from trigonal warping, but with the effective velocity 2 orders of magnitude lower, and so this finite width of the resonance, 0.6 millivolt, comes exactly from this.
My question concerns the mapping over the problem which you studied to the Cooper-Pebb problem. You simply changed the real interaction into a constant and obtained, of course, you obtained the Cooper-Pebb problem, and the result was as it is. But if you really take into account the character of the screening, there are Friedel oscillations, and you can map it onto Kohn-Lattinger superconductivity instead. What do you think about this?
I probably need to think more about this, but one thing I can say is that so on this graph you can see different curves, and they are basically some of our attempts to improve or this simple contact approximation for the interaction. So we didn't put one over Q. You are right that there is also Friedel oscillation contribution, although in single layer graphene, normally contributions from normal Friedel oscillations are suppressed because backscattering in graphene is suppressed, and Friedel oscillation comes from backscattering.